A brief introduction to the principles of gravity methods and their instruments. Gravity methods are among the most fundamental geophysical tools used to investigate the Earth's subsurface. By measuring natural variations in the gravitational field, gravity surveys reveal changes in density beneath the Earth's surface. These density changes correspond to geological structures such as faults, sedimentary basins, intrusions, ore bodies, cavities, and other features that differ in mass distribution. Fundamentals of gravity. Newton's law of gravitation. Gravity is the attractive force between any two masses. Newton's law is often written mathematically. The gravitational force is equal to the gravitational constant multiplied by the product of the two masses, and then divided by the distance between them squared. This describes how the force changes when mass or distance changes. Gravitational acceleration. The gravitational acceleration at Earth's surface is often described mathematically as gravitational acceleration is equal to the gravitational constant multiplied by the mass of the Earth, and divided by the radius of the Earth squared. The average value of gravitational acceleration at sea level is about 9.81 meters per second squared. Small variations occur due to latitude, elevation, tides, and subsurface density contrasts. Units in gravity surveys. Gravity is measured in meters per second squared. The gal is a common geophysical unit. 1 gal is equal to 1 centimeter per second squared. 1 milligal is 1,000th of a gal. 1 microgal is 1 millionth of a gal. Gravity anomalies in geophysics often range from 0.1 milligal to 100 milligals, requiring very precise instruments. Factors affecting gravitational measurements. Raw gravity readings must be corrected for several contributing factors. Latitude effects. Gravity increases toward the poles and decreases toward the equator due to Earth's rotation and its slightly flattened shape. This variation is accounted for using the International Gravity Formula. Free air correction. Gravity decreases with height. The free air correction compensates for this reduction when measurements are taken above sea level. Booger correction. The Booger correction accounts for the extra mass between the instrument and sea level. This correction assumes a slab of rock beneath the measurement point. Terrain correction. Terrain correction is needed when the local topography is irregular, such as mountains or valleys. It adjusts the Booger correction to account for nearby slopes and density variations. Tidal and instrument drift effects. Gravity changes slightly due to gravitational attraction from the Moon and Sun. Gravimeters also experience mechanical drift over time. These effects are removed through tidal models and repeated measurements at base stations. Gravity anomalies. After applying corrections, the remaining variations are called gravity anomalies. Types of gravity anomalies. Booger anomaly, commonly used in exploration, accounts for air, elevation, slab mass, and terrain. Free air anomaly, widely used in marine studies. Isostatic anomaly, used in large-scale tectonic or crustal studies. Positive and negative anomalies. A positive anomaly indicates a region with higher than average density, such as a dense intrusion or an ore body. A negative anomaly indicates lower than average density, such as sedimentary basins, salt domes, or voids. Gravity surveying methods. Land gravity surveys involve moving a gravimeter across predetermined stations. Used in engineering, mining, and hydrogeology. Marine gravity surveys use stabilized gravimeters on ships. Important for offshore oil and gas exploration. Airborne gravity surveys use aircraft-mounted gravimeters combined with inertial navigation systems. Useful for regional mapping, especially in remote areas. Principles of gravity instruments. Gravity instruments measure extremely small changes in gravitational acceleration. The main categories are absolute gravimeters, relative gravimeters, marine gravimeters, airborne gravimeters, superconducting gravimeters, absolute gravimeters. Principle of operation. Absolute gravimeters measure gravity directly by tracking the acceleration of a freely falling object. The principle can be stated as: gravity is determined by measuring how the position of a freely falling mass changes with time, and calculating the second derivative of position with respect to time. These instruments use a laser interferometer, and the falling mass is tracked extremely precisely. Advantages: provide absolute gravity values. Highly accurate. No drift. Limitations: expensive and not portable. Require vibration-free environments. Slow measurement rate. Relative gravimeters. Relative gravimeters measure the difference in gravity between locations. Mass spring principle. A mass is suspended by a spring. The gravitational force pulls the mass downward, and the spring provides an upward restoring force. The system is described verbally as: the gravitational force on the mass is equal to the spring constant multiplied by the spring's extension. Changes in gravitational acceleration cause tiny changes in the spring's length, which the instrument measures. Main types: Lacoste and Romberg gravimeters. User: zero-length spring. Very sensitive. Suitable for land, marine, and airborne use. Warden gravimeters. Older mechanical type. Less sensitive but still useful. Syntrex CG series, CG5, CG6. Modern digital gravimeters. Quartz springs and electronic detection. High precision and ease of use. Drift and calibration. Relative gravimeters drift over time due to spring relaxation. To correct this, surveyors visit known base stations multiple times per day. Advantages and limitations. Advantages: portable. High sensitivity. Good for detailed surveys. Limitations: only measure differences, not absolute values. Require drift correction. Sensitive to temperature and vibration. Marine gravimeters. Challenges: ships move in multiple directions, causing noise in gravity data. Specialized stabilization is required. Stabilized platforms. Marine gravity meters use gyroscopic or gimbal platforms to keep the instrument level even when the ship rolls or pitches. Principle: they are modified relative gravimeters with damping, motion sensors, and stabilization systems. Data processing. Marine gravity data needs several corrections, including the EOTWOS correction, which compensates for effects of ship velocity interacting with Earth's rotation. Airborne gravimeters. Purpose: used for wide area mapping, especially in inaccessible regions. Components typically include a spring mass gravity sensor, an inertial navigation system, differential GPS. Challenges: aircraft motion produces large accelerations. Advanced filtering and navigation systems are used to remove these effects. Performance: airborne gravity is less precise than land gravity but extremely efficient over large areas. Superconducting gravimeters. Principle: a small superconducting sphere is levitated in a magnetic field. Changes in gravity alter the electrical current needed to keep the sphere suspended. This change is measured with extraordinary precision. Applications: earth tides, hydrology, volcano monitoring, geodynamics. Limitations: need liquid helium, stationary, very costly. Modern advancements in gravity instruments. Cold atom interferometry uses clouds of ultra-cold atoms to measure gravity without drift. These instruments could revolutionize portable absolute gravity measurements. MEMS-based gravimeters. Micro-electromechanical gravimeters are small, inexpensive, and ideal for dense sensor networks, though currently less precise than spring mass systems. Applications of gravity methods. Mineral and petroleum exploration. Gravity helps detect sedimentary basin depths, mafic intrusions, dense metallic ore bodies, salt structures. Engineering and environmental. Used to detect cavities and voids, buried channels, landfill variations, foundation stability, hydrology and glaciology. Gravity changes track, groundwater storage, glacier mass balance, seasonal snow changes, regional geology in geodesy. Gravity is essential in studies of crustal thickness, isostatic compensation, lithospheric structure, data interpretation, density contrast. Gravity anomalies depend on density contrast, which can be spoken as changes in gravitational acceleration are proportional to changes in density. Depth estimation. Shallow bodies produce sharp anomalies, deeper bodies produce broader ones. Forward and inverse modeling. Forward modeling predicts what gravity anomaly a given geological structure would produce. Inverse modeling attempts to derive the structure from the anomaly. Non-uniqueness. Multiple density distributions can produce the same anomaly. Geological knowledge is essential for resolving this. Limitations of gravity methods. Non-unique solutions. Sensitive to noise. Requires extensive corrections. Density contrasts must be significant. Deep targets are harder to resolve. The gravitational field of the Earth and its variation in space and time. The gravitational field of the Earth is one of the most fundamental forces affecting everything on our planet, from the motion of satellites to the flow of ocean currents, from the drifting of tectonic plates to the simple act of walking. Although we usually think of gravity as a constant downward pull, the gravitational field is far from uniform. It varies from place to place across the globe, and it changes with time due to natural and human-driven processes. Understanding the gravitational field and its variations is essential for geodesy, satellite navigation, oceanography, climate studies, resource exploration, and many branches of earth science. What is the gravitational field? The gravitational field describes how the Earth pulls on masses. In simple terms, you can think of the gravitational field as a measure of how much gravitational acceleration acts on an object at a given point. On the Earth's surface, this gravitational acceleration is close to 9.8 meters per second squared, but the precise value depends on a variety of factors. Because gravity results from mass, any uneven distribution of mass inside the Earth or on its surface will influence the gravitational field. The gravitational field can be thought of as a three-dimensional map that shows how mass is arranged inside the planet. Areas where the gravitational acceleration is stronger indicate higher densities beneath the surface, while weaker areas indicate lower densities. Why the Earth's gravity is not uniform? Gravity would be uniform if the Earth were perfectly spherical, not rotating, internally homogeneous, free from mountains, oceans, ice sheets, or tectonic boundaries. But none of these conditions are true. As a result, the Earth's gravitational field varies both spatially, meaning from place to place, and temporally, meaning over time. The major causes of gravitational variation include the Earth's rotation, the Earth's slightly flattened shape, variations in surface topography, variations in subsurface density, ocean tides and atmospheric movement, groundwater and ice changes, tectonic processes, lunar and solar gravitational attraction. Each of these factors affects gravity in predictable or measurable ways. The shape of the Earth and its influence on gravity. The Earth's flattening at the poles. The Earth is not a perfect sphere. It is slightly flattened at the poles and bulging at the equator due to rotation. This shape is known as an oblate spheroid. Because gravity depends on the distance from the Earth's center, and because the poles are closer to the center than the equator, gravity is stronger near the poles, weaker near the equator. Furthermore, the centrifugal effect from rotation reduces gravity most at the equator and least at the poles. This contributes to the well-known geographic gradient in gravity. Gravity variation with latitude. If you traveled from the equator to the poles and measured gravity along the way, you would find a steady increase. This increase is caused by two combined effects. Decreased radius of the Earth toward the poles. Decreased centrifugal force as you move toward the poles. Although exact numeric values depend on precise formulas, The important point for audio clarity is that gravity is lowest at the equator and highest at the poles. Gravity variation with elevation. When you move upward away from the Earth's surface, either by climbing a mountain or using an aircraft, gravity decreases because gravitational attraction weakens with distance. This change is small but measurable. A commonly used conceptual relation, spoken in words, is gravitational acceleration decreases as the distance from the center of the Earth increases. In addition to this geometric effect, high mountains add local mass, affecting gravity in more complex ways. The influence of topography and mass distribution. Mountains and valleys. Mountains contain extra mass, which slightly increases gravity, but they also elevate the measuring point farther from the Earth's center. These two effects partly cancel. The net effect generally depends on the density of the rocks and the height of the terrain. Valleys, on the other hand, contain less mass, which tends to decrease the gravitational acceleration. Oceans. Ocean water is less dense than continental crust. This difference in density results in lower gravitational acceleration over deep oceans compared to continents. However, ocean tides move millions of tons of water, and these movements cause periodic gravitational variation. Subsurface density variations. The Earth's interior is layered and heterogeneous. Rocks vary widely in density. Sedimentary rocks are relatively light. Igneous and metamorphic rocks are denser. Metallic ore bodies can be extremely dense. Salt bodies are lighter than surrounding sediments. Because gravity responds to mass, subsurface structures such as sedimentary basins, plutonic intrusions, faults, and mineral deposits all affect the gravitational field. Dynamic causes of gravity variation. Through time, gravity not only varies across different regions, but it also changes with time. These temporal variations may be cyclic, gradual, or sudden. Tides generated by the Moon and the Sun. The gravitational attraction of the Moon and the Sun produces periodic changes known as Earth tides. These tides cause both deformation of the Earth's crust, movement of ocean water. Together, they create gravity changes that repeat every 12 hours, 24 hours, and on longer monthly and seasonal cycles. The magnitude of these changes is typically small but is easily measurable with modern gravimeters. Seasonal hydrological changes. Changes in groundwater storage, rainfall, snowpack, and soil moisture alter the mass near the surface. Because water is heavy, these changes can affect gravity. For example, during wet seasons, gravity increases slightly because water stored in the ground adds mass. During dry seasons, gravity decreases as water drains away or evaporates. Large aquifers may experience significant gravity changes due to pumping or natural recharge. Glacial and ice sheet changes. Ice sheets and glaciers hold enormous mass, and their growth or melting influences Earth's gravity. When ice melts, mass decreases locally, reducing gravity. Mass redistributes into oceans, altering regional gravity. Satellite missions such as the Gravity Recovery and Climate Experiment, often called GRACE, have measured these changes with great accuracy. Tectonic processes. Earthquakes, volcanic activity, and plate motions can all change gravity either suddenly or gradually. For example, a volcanic intrusion introduces new mass into the crust. An earthquake may shift blocks of crust, altering density distribution. Uplift or subsidence due to tectonic forces changes elevation and crustal mass distribution. These changes can be detected and monitored through repeated gravity measurements. Gravity variation due to Earth's internal structure. The crust. Gravity over continental crust differs from gravity over oceanic crust. Continental crust is thicker but less dense, whereas the oceanic crust is thinner but denser. The mantle. The upper mantle has variable density due to temperature differences and dynamic flow. Hot mantle is less dense and produces lower gravity signals, while the cool mantle is denser. The core. The Earth's core is extremely dense. Gravity measurements combined with seismic data reveal information about the size and density of the core. Although direct gravity variations from the core are not measured at the surface, the overall gravitational field gives insight into Earth's internal mass distribution. The geoid, a gravity-based reference surface. One of the most important concepts related to Earth's gravity is the geoid. The geoid is an imaginary surface that corresponds to mean sea level, is perpendicular everywhere to the gravitational direction, is irregular in shape due to variations in Earth's mass distribution. The geoid undulates up and down relative to a simple mathematical ellipsoid. These undulations represent gravitational highs and lows. Areas where the geoid is higher correspond to regions with greater underlying mass or density. Areas where the geoid is lower correspond to regions of lower mass. Measuring and mapping the geoid is essential for navigation, satellite orbit calculation, elevation measurement, and oceanography. Measuring gravity and gravitational variations. Understanding how Earth's gravitational field changes requires precise instruments and methods. Absolute gravimeters. Absolute gravimeters measure gravitational acceleration directly by tracking a freely falling mass. The principle is, gravitational acceleration is determined by measuring how fast the position of a falling object changes with time. These instruments provide highly accurate baseline measurements. Relative gravimeters. Relative gravimeters measure the difference in gravity between points. They use a mass suspended by a spring. When gravity changes, the extension of the spring changes slightly. The principle is, the gravitational force pulling on the mass is balanced by the spring force, and the change in spring length indicates the change in gravitational acceleration. These instruments are widely used in field surveys. Superconducting gravimeters. These instruments levitate a superconducting sphere in a magnetic field. Small changes in gravity cause the sphere to move very slightly, and these movements are detected with extraordinary precision. Superconducting gravimeters are used for long-term monitoring of earth tides, groundwater changes, and other subtle processes. Satellite gravity missions. Modern satellite missions have revolutionized the study of Earth's gravity. The GRACE mission. GRACE stands for Gravity Recovery and Climate Experiment. Two satellites follow each other in orbit. Changes in gravity cause tiny differences in their separation distance. These differences allow scientists to map gravitational variations. GRACE has been used to measure melting of the Greenland and Antarctic ice sheets, depletion of major aquifers, changes in ocean mass, post-glacial rebound of the crust. The GOCE mission. GO stands for Gravity Field and Steady-State Ocean Circulation Explorer. It measured tiny changes in gravity using sensors that detected differential accelerations within the satellite. GOCE produced one of the most accurate maps of the Earth's geoid. Spatial variations in Earth's gravity. Spatial variations arise from latitude, elevation, topography, subsurface density, ocean depth, ice thickness, tectonic setting, large-scale variations. Examples of large-scale gravity features include higher gravity over ocean basins due to denser crust, lower gravity over continental plateaus, distinct gravitational signatures of mid-ocean ridges, gravity lows in deep sedimentary basins, local variations. Local variations may be caused by ore bodies, volcanic intrusions, faults, karst or void zones. Small gravity changes can reveal important subsurface features useful in exploration and engineering. Temporal variations in Earth's gravity. Temporal variations happen on many timescales. Hourly to daily changes. Earth tides caused by the moon and sun. Atmospheric pressure variations. Ocean tide loading. Seasonal changes. Snow accumulation and melting. Soil moisture changes. Groundwater recharge and discharge. Yearly to decadal changes. Ice sheet thinning. Long-term aquifer depletion. volcanic inflation or deflation, geological timescale changes, post-glacial rebound, mantle convection, plate tectonic motions. These processes produce extremely slow but measurable adjustments in gravity. Applications of understanding gravity variations. Geodesy in navigation. Gravity models are essential for satellite orbit determination, elevation measurement, GPS accuracy improvement, climate science. Gravity measurements help quantify ice mass loss, ocean circulation changes, groundwater depletion, resource exploration. Gravity surveys reveal sedimentary basin depth, dense ore deposits, salt domes, earthquake and volcanic monitoring. Changes in gravity can signal magma movement, fault zone changes, crustal deformation, hydrology and environmental studies. Gravity helps track water movement at regional and continental scales. The future of gravity studies. New technologies will enhance our ability to measure gravity. Cold atom gravimeters. These instruments use clouds of atoms cooled to extremely low temperatures. Their movement reveals gravity with very high accuracy. They offer drift-free performance, ideal for long-term monitoring. Quantum sensors. Quantum technologies are being developed to detect even smaller gravity changes, allowing improved monitoring of groundwater, volcanic activity, and tectonic processes. Next generation satellites. Future missions will continue tracking ice loss, sea level rise, and water cycle changes. They will provide higher spatial resolution and longer mission lifetimes. The International Gravity Formula and factors contributing to gravity variation on the Earth's surface. Gravity is one of the most fundamental forces acting on the Earth. It controls the motion of oceans and the behavior of the atmosphere, shapes Earth's surface, governs satellite orbits, influences tectonic processes, and affects every aspect of life. Although gravity is often taken for granted as a constant downward force, the actual gravitational acceleration at the Earth's surface varies from one location to another due to several physical and geological factors. To describe how gravity changes with latitude and elevation, scientists developed what is known as the International Gravity Formula. This formula provides a theoretical or normal value of gravity at sea level for any latitude on Earth. It acts as a reference against which real gravity measurements are compared. Because real measurements deviate from this theoretical value due to local and regional geological differences, the International Gravity Formula is essential for interpreting gravity surveys, geodesy, satellite navigation, oceanography, and global Earth science research. Why a standard, normal, gravity value is needed? Gravity measurements around the world vary due to many influences. These include latitude, elevation, Earth's rotation, shape of the Earth, subsurface density, mass distribution at and below the surface, temporal effects such as tides. Because of these variations, raw gravity measurements taken at different places cannot be compared directly. A measurement taken in Canada, for example, cannot be interpreted without knowing what the theoretical gravity at that latitude should be. Similarly, measurements taken near the equator must be compared using a standard reference for equatorial gravity. The International Gravity Formula provides this essential reference. It gives the normal gravitational acceleration at sea level at any latitude, assuming the Earth is an ideal oblate spheroid. The density is radially symmetric. Only the effects of latitude and rotation are considered. This allows scientists to calculate a standard gravity value, which is then compared with actual measurements to determine local anomalies. The concept behind the International Gravity Formula. Gravity depends on latitude. One of the most important contributions to the International Gravity Formula is the variation of gravity with latitude. Gravity is stronger at the poles and weaker at the equator. This happens for two main reasons. Earth's rotation. The Earth spins around its axis once every 24 hours. This rotation creates a centrifugal effect, which acts outward from the axis of rotation. This centrifugal effect is strongest at the equator and zero at the poles, because the equator is farthest from the axis of rotation. This outward effect slightly reduces gravitational acceleration at the equator. In spoken form, as you move from the poles toward the equator, the outward centrifugal effect increases and reduces the effective gravitational acceleration. Earth's flattened shape. The Earth is not perfectly spherical. It is flattened at the poles and bulges at the equator. This shape is known as an oblate spheroid. Because the poles are closer to the center of the Earth than the equator is, gravitational acceleration is naturally higher at the poles. Combined with the effects of rotation, this produces a smooth increase in gravity from the equator toward the poles. Gravity depends on elevation. The International Gravity Formula primarily describes gravity at sea level, but real measurements often occur above or below this level. As elevation increases, the distance from the center of the Earth increases, which reduces gravity. In spoken terms, gravitational acceleration decreases as the distance from the center of the Earth increases. For this reason, elevation corrections such as the free air correction and the Booger correction are applied in gravity surveys, but those are separate from the International Gravity Formula itself. The International Gravity Formula explained as. The International Gravity Formula has been revised multiple times as measurements improved. Although several versions exist, the most commonly used is known as the International Gravity Formula of 1967, also called the Geodetic Reference System 1967 value. The normal gravitational acceleration at sea level at a given latitude is equal to 9.780317 meters per second squared, plus 0.005290 times the square of the sine of the latitude. In other words, you take a constant base gravity value. Add a term that depends on the sine of the latitude squared. This expression captures the idea that gravity increases toward the poles. Later refinements, such as the International Gravity Formula of 1980, include even more precise coefficients, but the concept remains the same. They all describe how normal gravity depends on latitude due to Earth's shape and rotation. Factors that contribute to gravity variation on the Earth's surface. Gravity at any location on Earth differs from the normal gravity predicted by the International Gravity Formula. These differences are called gravity anomalies, and they arise from many physical and geological factors. Factor 1. Latitude. Latitude has the single largest predictable effect on gravity. As previously described, gravity is lower at the equator. Gravity increases gradually toward the poles. The key reasons are Earth's shape and rotation. The International Gravity Formula incorporates latitude explicitly, so this contribution is well understood and predictable. Factor 2. Elevation or height above sea level. Elevation affects gravity because gravity becomes weaker as the measurement point moves farther from the Earth's center. A simple spoken description is: gravity decreases when elevation increases. Examples. Gravity measured on top of Mount Everest is smaller than gravity at sea level. Gravity at sea level is larger than gravity at the top of a high plateau. In high mountains, the reduction in gravity due to elevation is partly offset by the mass of the mountains themselves, which increases gravity. This leads to the need for additional corrections such as free air correction, Booger correction. But elevation itself is a fundamental factor independent of terrain mass. Factor 3. Topographic mass. Topographic masses, mountains, hills, plateaus, deep valleys, and basins, affect gravity because they change the amount of mass near the measurement point. Large mountains increase gravity because they add mass. Deep valleys decrease gravity because mass has been removed. However, this effect is complicated by elevation, and both must be considered together. Factor 4. Subsurface density variations. One of the most important contributors to gravity variation is the density of rocks below the surface. Different rock types have different densities. Sedimentary rocks are relatively light. Volcanic and metamorphic rocks are heavier. Dense metallic ore bodies are much heavier. Salt structures are lighter. Because gravity responds to mass, regions with higher rock density produce higher gravity values, and regions with lower density produce lower gravity values. Examples: a buried granite intrusion will create a positive gravity anomaly. A large sedimentary basin will create a negative gravity anomaly. A salt dome will produce a strong negative anomaly because salt is light. These subsurface density differences are the foundation of gravity methods in mineral and petroleum exploration. Factor 5. Earth's rotation. Earth's rotation produces an outward centrifugal effect, which reduces the effective gravity felt at the surface. This effect varies with latitude. Strongest at the equator, zero at the poles. This centrifugal effect is one of the primary reasons the International Gravity Formula includes a latitude term. Because the Earth spins, there is a small outward acceleration that reduces the apparent gravitational pull. This outward effect is largest at the equator and decreases to zero at the poles. Factor 6. Temporal variations such as Earth tides. Gravity changes over time due to the gravitational attraction of the Moon and the Sun. These changes are called Earth tides. They cause both deformation of the Earth, movement of ocean water. This leads to periodic increases and decreases in gravity throughout the day. The gravitational pull of the Moon and the Sun causes the Earth to stretch and relax slightly, which modifies gravity on cycles of about 12 hours and 24 hours. These changes are typically small but measurable with modern instruments. Factor 7. Ocean tides and mass redistribution. Because ocean water moves continuously, so does the mass distribution on Earth's surface. When tides rise, the increased water mass raises gravity slightly in coastal regions. When tides fall, gravity decreases slightly. Large-scale ocean circulation also redistributes mass and contributes to long-term gravity changes. Satellite missions such as GRACE have measured these variations. Factor 8. Groundwater and hydrological effects. Water stored underground contributes mass. As groundwater increases due to rainfall or snowmelt, local gravity increases. As groundwater is pumped or drained, gravity decreases. Examples: large irrigated agricultural areas show seasonal gravity changes. Aquifers used for drinking water can show long-term gravity decline as water is extracted. These hydrological effects are crucial for monitoring water resources using gravity measurements. Factor 9. Ice sheets and glaciers. Ice sheets contain tremendous mass. When they melt due to climate change, gravity over these regions decreases. Meanwhile, gravity increases in the oceans where the melted water accumulates. When ice melts, mass is removed from the land and added to the oceans, and this redistribution changes gravity across the globe. Satellite observations have revealed major gravity decreases over Greenland and Antarctica over the past decades. Factor 10. Tectonics, volcanoes, and crustal deformation. Tectonic processes change gravity by altering elevation, density structure, crustal mass distribution. Examples: uplift of mountain ranges reduces gravity due to increased elevation but increases gravity due to added rock mass. Volcanic magma movement changes gravity as magma intrudes or drains. Earthquake slip can change gravity instantly by redistributing rock mass. Gravity monitoring is widely used in volcano observatories to detect magma movement. How the International Gravity Formula is used in practice. The International Gravity Formula is used to compute the normal gravity value at the latitude of the measurement site. Real gravity measurements are then compared with this normal value to determine the gravity anomaly. This anomaly represents the difference between What gravity would be if the Earth were perfectly smooth and uniform, versus what gravity actually is at that location. Gravity anomalies are essential for mineral exploration, oil and gas exploration, engineering projects, geodetic reference systems, satellite orbit correction, ocean circulation modeling. Without the international gravity formula, gravity anomalies could not be accurately interpreted. Evolution of the international gravity formula. Several versions of the formula have been developed over time, including the 1930 formula, the 1967 formula, the 1980 formula from the Geodetic Reference System. Each update used improved measurements and a better understanding of Earth's size, shape, and rotation. The 1980 version is the most accurate and widely used today, especially in satellite-based Earth science. The basic spoken structure of these formulas remains the same. Gravity at sea level at a given latitude is equal to a constant baseline value plus additional terms that depend on the sign of the latitude squared, all expressing the effect of Earth's rotation and shape. Summary of all contributions to gravity variation. To summarize the key factors, spoken succinctly. Latitude. Gravity increases toward the poles. Elevation. Gravity decreases with increased height above sea level. Earth's rotation creates an outward centrifugal effect that reduces gravity, strongest at the equator. Earth's shape. The Earth's flattened shape at the poles increases gravity there. Topography. Mountains add mass and can increase gravity. Valleys reduce mass and decrease gravity. Subsurface density. Denser rocks produce higher gravity. Lighter rocks produce lower gravity. Earth tides. Caused by the moon and the sun, producing periodic gravity variations. Ocean tides. Water movement redistributes mass and changes gravity locally. Hydrological changes. Groundwater, soil moisture, and snow affect gravity. Ice sheet changes. Ice mass gain or loss influences gravity regionally and globally. Tectonic processes. Uplift, subsidence, magma movement, and earthquakes alter gravity. The international gravity formula addresses mainly the first two predictable factors, latitude and elevation at sea level. All other factors create anomalies that must be studied separately. The concept of gravity anomalies and microgravity anomalies. Imagine you are standing on the surface of the Earth, and someone asks, how strong is gravity right here, at this exact spot? Your first reaction might be, well, 9.8 meters per second squared. That's gravity. And you'd be mostly right. But that's only part of the story. The truth is something far more fascinating. Gravity is not perfectly uniform across the Earth. It varies from place to place, sometimes by a noticeable amount, sometimes by extremely tiny amounts that require sensitive instruments to detect. These variations in the strength of gravity are what scientists call gravity anomalies, and when those variations are extremely small, far smaller than everyday gravitational differences, we call them microgravity anomalies. Today, I'm going to take you on a deep, intuitive, narrative-style exploration of what these anomalies are, why they exist, how we detect them, and why they matter for everything from geology to archaeology to exploring distant planets. So let's begin. Gravity is not the same everywhere. We tend to think of Earth's gravity as a single number, about 9.8 meters per square second. But that's only an average. In reality, Earth's gravity varies due to a handful of major factors. Earth isn't a perfect sphere, it's an oblate spheroid, slightly wider at the equator and flattened at the poles. Earth's rotation creates centrifugal force, effectively reducing gravity slightly at the equator relative to the poles. Earth's internal structure is not uniform. Some regions are denser or less dense. Topography affects gravity. Mountains, valleys, oceans, and even deep mantle structures change the gravitational pull. Crustal thickness varies, creating regions of excess or deficit mass. Now, Each of these factors contributes to local variations in the gravitational field. You might find that gravity in the Himalayas is a little lower than expected, despite the massive mountains. Because the crust beneath the mountains is unusually thick and floats higher, a concept called isostasy. Or you might find that gravity above dense rock formations, ancient cratons, or underground ore deposits is slightly higher. Every one of these differences is a gravity anomaly. What is a gravity anomaly? Let's define it clearly. A gravity anomaly is the difference between the observed value of gravity at a location and the theoretical, expected, value if Earth were perfectly uniform and smooth. We have two parts here. Observed gravity, what an instrument, typically a gravimeter, actually measures at a location. Theoretical or reference gravity, what we would calculate for that latitude, altitude, and idealized Earth model. An anomaly exists when these two numbers don't match. If gravity is stronger than expected, right pointing arrow, positive anomaly. If gravity is weaker than expected, right pointing arrow, negative anomaly. These anomalies are not mistakes or measurement errors, they're signals. They tell us that something about the mass distribution beneath us is different than the model predicts. The physics behind gravity anomalies. To understand gravity anomalies intuitively, think of gravity as being directly tied to mass. More mass equals stronger gravitational pull. Less mass equals weaker gravitational pull. Let's look at two everyday analogies. Analogy 1. Thick vs thin mattress. Imagine you are lying on a mattress. Beneath parts of it, someone places heavy books. In other parts, they place soft pillows. If you press down with your hand at different spots, you feel the difference. Some spots push back more, dense regions, others less dense. Gravity anomalies work the same way. Your gravity probe feels more pull where the Earth is denser and less when it's less dense. Analogy 2. Patchy Earth. Picture a giant patchwork quilt where each square has different weights sewn into it: lead blocks, feathers, sandbags. When you lift the quilt, some squares feel heavier. Earth's crust and mantle are like that quilt, heterogeneous, variable, dynamic. A gravity anomaly is simply the measurement of these hidden patches. Types of gravity anomalies. Gravity anomalies aren't all the same. In geophysics, we classify them based on how we correct for predictable influences. Here are the key types. Free air gravity anomaly. This is the difference between observed gravity and the theoretical gravity without removing the effect of elevation. Why does elevation matter? The farther you are from Earth's center, the weaker gravity becomes. So we correct the measured value by adding a free air correction to account for the elevation difference. Free air anomalies are useful for studying large-scale tectonics, like uplifted mountain ranges or subsiding basins. Booger gravity anomaly. The Booger anomaly goes a step further. It not only corrects for elevation but also removes the gravitational effect of the terrain, the mountains, hills, valleys, by subtracting the gravitational effect of the mass between the measurement point and sea level. This gives a value that reflects density variations beneath the surface, not just topography. If you want to map what's happening in the crust and upper mantle, Booger anomalies are the way to go. A positive Booger anomaly usually means dense rock underneath. A negative one suggests less dense materials, like sedimentary basins. Terrain-corrected Booger anomaly, complete Booger anomaly. This is the most refined type, correcting for local topographic variations, like nearby mountain peaks or deep valleys, that simpler models ignore. This type is often used in mineral exploration, geothermal surveys, and detailed crustal mapping. What do gravity anomalies tell us? This is where things get fun. Gravity anomalies allow us to infer hidden structures underground. They are like X-rays of the Earth, except instead of radiation, we are using subtle changes in gravitational pull. Some common things we can detect: ore bodies and mineral deposits. Dense rocks like iron ore create strong positive anomalies. Salt domes. Salt is less dense than typical rock, so it creates negative anomalies. Detecting these is vital in oil exploration. Sedimentary basins. Large basins filled with low density sediment show significant negative anomalies. Tectonic boundaries and faults. Sudden changes in crustal structure are associated with shifts in gravitational strength. Volcanic structures. Magma chambers, lava tubes, and volcanic edifices create distinctive signatures. Subglacial features. Gravity anomalies help map bedrock beneath ice sheets. Gravity anomalies even help us understand the overall shape of the Earth, the dynamics of plate tectonics, and the structure of the mantle. Enter microgravity, the world of tiny changes. Now, let's shrink our focus. What happens when we want to detect gravitational differences not on the scale of kilometers or hundreds of meters, but on the scale of buildings, tunnels, voids, or subsurface cavities? This is where microgravity anomalies come into play. Microgravity refers to very small variations in gravity, typically on the order of microgals. 1 microgal equals 1 millionth of a gal. 1 gallon equals 1 centimeter per square second. Earth's gravity equals approximately 980,000 milligals. So a microgravity anomaly is extraordinarily tiny, literally a few parts per billion of the total gravitational field. But these small signals can reveal features that affect mass distribution on a much smaller scale. Hidden tunnels, underground voids, sinkholes, buried archaeological structures, caves, buried utilities, small near-surface ore bodies, subsurface contamination plumes, local changes in soil density. Microgravity surveys are often used in engineering site studies, environmental investigations, archaeology, volcanology, urban geology, geotechnical studies. Microgravity is basically gravity anomalies in high resolution. How do we measure microgravity? To detect such tiny variations, we need incredibly sensitive instruments. There are two main types. 1. Absolute gravimeters. These instruments measure gravity directly by timing the free fall of a small object, often with lasers. They give a precise absolute value of gravity at a location. But they are expensive, bulky, not ideal for rapid surveys. Relative gravimeters. These are much more common in field surveys. They measure the difference in gravity between points. Most microgravity surveys use spring-based or superconducting gravimeters that detect minute changes in the stretching of a spring or levitation of a superconducting sphere. Even footsteps or wind vibrations can disturb the readings. That's why surveys must be done carefully. Ground vibrations minimized. Temperature controlled. Repeated readings taken. Drift corrections applied. Microgravity surveys often involve hundreds of closely spaced measurement points to create detailed gravity maps. What causes microgravity anomalies? Let's explore a few examples in story format. Case 1. Detecting a cave beneath a parking lot. Imagine a construction company preparing to build on a large flat piece of land. The geological report suggests the region might have limestone caves. A cave is essentially a volume of missing mass, so the gravitational pull above it is slightly less. A microgravity survey detects this as a tiny negative anomaly, maybe just a few microgals. But that's enough to identify the risk before construction begins. Case 2. Identifying a hidden tunnel. In archaeology or security-focused projects, microgravity surveys can reveal man-made, underground tunnels. The absence of mass, the tunnel, shows up as a localized gravity low, allowing researchers to pinpoint features without excavation. Case 3. Monitoring a volcano. Volcanologists sometimes use microgravity to monitor how magma is moving beneath a volcano. If magma pulses upward into a chamber, that adds mass and creates a positive microgravity anomaly. If the chamber empties, gravity decreases. Monitoring these changes can offer early warnings of volcanic activity. Gravity anomalies vs. microgravity anomalies. The key differences. Let's summarize. Feature: gravity anomalies, microgravity anomalies. Scale: regional or large scale, kilometers to hundreds of kilometers, local or fine scale, meters to tens of meters. Magnitude: milligauss to tens of milligauss, microgauss, millionths of a gauss. Causes: crustal variations, tectonics, mantle density, mountains, basins, voids, caves, tunnels, small density changes. Instruments: standard gravimeters, satellite gravimetry, ultra-sensitive gravimeters. Applications: geology, tectonics, resource exploration, engineering, archaeology, structural studies. Data resolution: cause a very high resolution. Microgravity is essentially a special, ultra-detailed subset of gravity anomaly studies. Why do gravity and microgravity studies matter? You might be wondering, why go through all this trouble? Why measure such small differences? Here's why. In earth sciences, gravity anomalies help us understand the thickness of the crust, the structure of tectonic plates, the distribution of mountain roots, mantle convection patterns, subduction zones, hotspots, and volcanic systems. These are fundamental to how our planet works. In resource exploration, gravity surveys are indispensable in oil and gas exploration, mineral exploration, mapping sedimentary basins, locating dense ore bodies. For example, some iron ore deposits were discovered largely through gravity anomalies. In engineering and construction, microgravity surveys ensure buildings aren't constructed over voids. Bridges and dams sit on stable foundations. Sinkholes are detected before failure. In archaeology, without digging, gravity surveys can reveal buried structures, tombs, tunnels, foundations, chambers. This non-destructive method preserves important heritage sites. In planetary science, gravity anomalies are used to map Mars crust, the moon's mass concentrations, the internal structure of asteroids, ice thickness on icy moons like Europa. The Apollo missions discovered massive lunar anomalies, huge areas of denser rock beneath impact basins. Real-world examples. Let's look at a few famous examples. A. The Himalayas' surprising negative gravity anomaly. You'd think the Himalayas, with their massive mountains, would create a strong positive anomaly. But the opposite is true. Because the crust is so thick and floats higher due to buoyancy, the overall mass beneath the region is less dense than you would expect. This produces a long wavelength negative anomaly. B. The Chicxulub impact crater. The crater left by the asteroid that wiped out the dinosaurs is mostly buried. But gravity surveys revealed a circular gravity anomaly that helped researchers pinpoint its diameter and structure. C. Microgravity locates hidden tunnels at archaeological sites. At sites in Egypt, Mexico, and Turkey, microgravity has helped detect chambers and tunnels without disturbing the surface. These discoveries were later confirmed through careful excavation. How a gravity survey works, step by step. Let me walk you through a typical survey so you can picture the process. Step 1. Planning. Scientists study the geology, choose survey lines, and determine how closely spaced the measurements need to be. Large-scale surveys might space readings several kilometers apart. Microgravity surveys might use a grid of readings every few meters. Step 2. Field measurement. A gravimeter is placed at each measurement point. The operator levels the instrument, allows it to stabilize, records several readings, notes temperature, time, and location. It might take 5 to 10 minutes per measurement in a microgravity survey, or longer in sensitive environments. Step 3. Data corrections. Raw gravity readings are influenced by many factors, so several corrections are applied. Drift correction. Instruments drift slowly. Latitude correction, gravity varies with latitude. Free air correction, elevation. Booger correction, mass between sensor and sea level. Terrain correction, nearby topography. Tidal corrections, gravity changes as the moon and sun tug on Earth. Yes, gravity data is so sensitive that the tides must be mathematically removed. Step 4. Building maps. Corrected data is turned into gravity maps, profiles, contour plots, 3D models. These maps show gravity highs and lows that correspond to subsurface features. Step 5. Interpretation. Geophysicists analyze the patterns. A long smooth low might indicate a sedimentary basin. A sharp high might reveal a dense intrusion. A tiny localized low might indicate a cave or void. Models are tested using geology, seismic data, and sometimes drilling. Limits and challenges of gravity and microgravity. Gravity methods are powerful, but not perfect. Gravity is non-unique. A single anomaly can be produced by many possible subsurface shapes. Extra data is needed to constrain the interpretation. Noise and interference. Microgravity surveys are easily affected by traffic, footsteps, temperature changes, local vibrations. This makes data quality a challenge. Resolution limits. Gravity surveys cannot resolve extremely small or very deep features unless the mass contrast is large. Why gravity will always matter. Even with new geophysical technologies, like drones, ground-penetrating radar, and deep seismic imaging, gravity remains fundamental. Here's why. It directly measures mass, something no other ground-based method does. It's non-invasive and environmentally gentle. It scales from global to microscopic. It's cost-effective compared to massive seismic operations. It works on Earth, the Moon, Mars, and beyond. Gravity is one of our best remote sensing tools for understanding the hidden layers of the world around us. Final summary. Let's wrap this up in the tone we began with. Gravity anomalies and microgravity anomalies are essentially clues. Tiny whispers from the Earth telling us what lies beneath our feet. They reveal differences in density, structure, and mass that we can't see with our eyes. A gravity anomaly is a mismatch between what gravity should be and what we actually measure. A microgravity anomaly is a much smaller version of the same thing, revealing subtle features like caves, voids, tunnels, and small density changes. Together, they help us explore for minerals and oil, map tectonic plates, understand volcanic systems, build stable infrastructure, discover archaeological treasures, study other planets and moons. Gravity is everywhere, but it isn't the same everywhere. And by studying its small variations, we uncover the hidden architecture of our planet.